Welcome to Podcast Learn and Fun. Let's start today's journey of learning about something called a determinant.
A determinant.
Now, I know what you might be thinking, determinant. That sounds a bit technical, maybe even a little intimidating.
Yeah.
But stick with me because determinants are way more fascinating than they might first appear. They're like hidden keys that unlock a deeper understanding of matrices and their amazing properties.
You see, matrices are these powerful tools for representing data and transformations in a structured way. And every square matrix, the kind with the same number of rows and columns, has this special number associated with it called its determinant. It's not just some arbitrary value.
Right.
It tells us a lot about the matrix's behavior and its effects on things like space and transformations.
Okay, I'm intrigued. So how do we calculate this secret code, this determinant, and what kind of secrets does it reveal?
Well, there are a few ways to calculate a determinant. The one common method is called cofactor expansion.
Cofactor expansion.
It's a bit like a detective carefully piecing together clues. You break down the matrix into smaller and smaller pieces until you get to something manageable.
Yeah.
Each element in the matrix has a corresponding cofactor, which is like a mini determinant, and these cofactors help us calculate the overall determinant.
So it's a process of systematically breaking down complexity, kind of like solving a puzzle by focusing on individual pieces.
Exactly. And what's really cool is that the single number, the determinant, can instantly tell us whether a matrix is invertible.
Okay.
You see, some matrices have an inverse, a sort of mirror image that reverses their effects, but not all matrices are invertible.
Right.
And the determinant acts as a litmus test if it's zero. The matrix is singular, meaning it has no inverse. If the determinant is non-zero, we know the matrix is invertible.
It's like having a special key that only works on certain locks. A non-zero determinant is like the right key, allowing us to unlock the inverse.
And here's where it gets even more interesting. Determinants aren't just about algebraic manipulations. They have a deep connection to geometry. Think about a simple 2x2 matrix. Its determinant actually represents the area of a parallelogram formed by its column vectors.
Wait a minute, we're talking about shapes now. So this number calculated from a matrix of numbers can tell us something about the physical space enclosed by its vectors.
It's a remarkable connection, and it extends to higher dimensions as well. Imagine a 3x3 matrix. Its determinant represents the volume of a parallel pipe formed by its column vectors. It's like the matrix is encoding information about the space its vectors are defining.
That's amazing. It's like this single number, the determinant, is a bridge between the abstract world of algebra and the visual world of geometry. It's like a secret code that reveals the hidden geometry within a matrix. So a determinant of zero would mean the shape collapses like a deflated balloon.
Precisely. A zero determinant indicates that the vectors are linearly dependent, meaning they're all confined to a lower dimensional space. That's why the geometric shape associated with the matrix loses its volume or area.
This is blowing my mind. We have gone from secret codes to keys and locks to geometric shapes, and it's all connected through this single powerful concept of the determinant. I'm starting to grasp the profound implications this has for understanding how matrices work.
And there's so much more to explore. For example, determinants exhibit fascinating properties that reveal even deeper insights into matrix behavior.
Okay, I'm hooked. What other secrets are these determinants hiding?
One of the most useful properties is the multiplicative property. It tells us that if you multiply two matrices together, the determinant of the resulting matrix is simply the product of their individual determinants.
So it's like each matrix has its own scaling factor represented by its determinant. When you combine them, you're essentially multiplying those scaling factors together.
Precisely. This has profound implications in fields like computer graphics and robotics, where understanding the cumulative effect of multiple transformations is crucial. Imagine designing a robot arm that needs to move through a complex series of rotations and translations. Determinants help us model and control those movements accurately.
So we're not just talking about abstract mathematical concepts. We're talking about tools that have real-world applications in designing and controlling systems.
Absolutely. Now, another fascinating aspect of determinants is how they're affected by row and column operations. We can manipulate matrices in a few key ways: swapping rows, multiplying rows by a scalar, or adding a multiple of one row to another. These operations are like rearranging the building blocks of the matrix, and each operation has a predictable effect on the determinant.
It's like our detective is using different techniques to analyze the clues, each revealing something new about the case. But wouldn't changing the matrix change its fundamental properties?
That's the beauty of it. While these operations change the appearance of the matrix, they don't change its essence, its underlying nature as captured by the determinant. For example, swapping two rows flips the sign of the determinant. Multiplying a row by a scalar scales the determinant by the same factor, but adding a multiple of one row to another doesn't change the determinant at all.
So it's like rearranging furniture in a room. The room size stays the same even though the layout has changed. These operations give us a way to manipulate the matrix without altering its fundamental character.
Exactly. And this leads us to some clever computational strategies for calculating determinants, especially for large matrices where direct cofactor expansion can become unwieldy. One strategy is row reduction, also known as Gaussian elimination.
I've heard of Gaussian elimination, but I always thought it was just for solving systems of equations. How does it help us calculate determinants?
It's a powerful technique that lets us transform a matrix into a special form called upper triangular form, where all the entries below the main diagonal are zero. The determinant of an upper triangular matrix is simply the product of its diagonal entries, making the calculation a breeze.
So it's like we're simplifying the matrix, revealing its structure in a way that makes the determinant easy to calculate. We're not changing the underlying information, just making it more accessible.
Precisely. And then there's another method called LU decomposition, which breaks down a matrix into two simpler matrices, a lower triangular matrix and an upper triangular matrix.
So we're essentially factoring the matrix. Is that like finding the prime factors of a number?
That's a great analogy. And just like with row reduction, the determinant of the original matrix is simply the product of the determinants of those two triangular matrices. LU decomposition is especially useful when you need to perform multiple calculations with the same matrix, as the factorization can be reused.
It's like having a pre-assembled toolkit ready to go. We don't have to start from scratch every time. I'm amazed by how much depth and versatility there is to this concept of a determinant.
And this is just scratching the surface. Determinants have profound implications in various fields, from solving systems of linear equations to analyzing complex transformations in physics and engineering. For example, in quantum mechanics, determinants are used to calculate the wave function of a system which describes the probability of finding a particle in a particular state.
Wow. So from robotics to the quantum realm, determinants are everywhere. But I have to admit, I'm still a bit hazy on how they're used to solve systems of equations.
Well, imagine you have a system of linear equations, each representing a constraint or relationship between variables. You can represent these equations in matrix form, and the determinant of that matrix tells you if the system has a unique solution.
So a non-zero determinant means we can find a unique solution. But a zero determinant means either there are no solutions or infinitely many solutions. It's like the determinant is telling us whether the system of equations makes sense or is contradictory.
Exactly. And this has applications in various fields like economics, where you might use systems of equations to model supply and demand or to analyze market equilibrium.
This is incredible. I'm starting to see how determinants aren't just abstract mathematical curiosities, but powerful tools for understanding and solving real-world problems.
And that's just one example. Determinants also play a crucial role in eigenvalue problems.
Eigenvalue problems.
Eigenvalues are special values associated with a matrix that reveal its fundamental modes of behavior, and determinants are essential for calculating them. This has implications in fields like machine learning, where eigenvalues are used in dimensionality reduction techniques like principal component analysis.
So determinants are helping us uncover the hidden patterns and structures within complex data sets. It's like they're giving us a way to see the forest for the trees.
Exactly. And let's not forget about their role in understanding transformations. Remember how we talked about determinants representing the scaling factor of a transformation? Well, they can also tell us whether a transformation preserves orientation or flips it.
So a positive determinant means the transformation is like a mirror image, reversing the orientation. It's fascinating how this single number can capture so much geometric information.
It truly is. And as you delve deeper into linear algebra, you'll find determinants appearing in all sorts of unexpected places. They're like a recurring theme, a unifying thread that connects different concepts and reveals the elegance and power of matrices.
It's incredible how this one number, the determinant, can reveal so much about a matrix's character. It's like having a secret decoder ring for the language of linear algebra.
And that's precisely what makes determinants so fundamental to linear algebra and its applications. They bridge the gap between algebra and geometry, giving us a deeper understanding of how matrices work and how they transform space.
From invertibility and scaling to areas, volumes, and even the effects of different matrix operations, Determinants are like a Swiss Army knife for matrix analysis. They give us the tools to unlock a whole new level of understanding.
So as you continue to explore the world of linear algebra, remember the power of the determinant. It's a key that opens many doors, revealing the intricate beauty and elegance of matrices.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.